Picture this right now. As you're watching this video, billions upon billions of atoms are arranged in specific patterns to form your body, your phone, the air you're breathing. And if someone asked you to describe what one of these atoms looks like, you'd probably sketch out something familiar. A central core with tiny objects whizzing around it in predictable loops. Am I right? That mental image lives in your head because it's been drilled into you since elementary school. Every textbook, every diagram, every educational poster shows the same thing. It's comfortable, it's simple, it makes sense, and it's a complete fabrication. I'm not exaggerating for effect here. The model you've been taught, the one that feels so obvious and intuitive, isn't just slightly inaccurate or a useful approximation. It's fundamentally disconnected from reality in ways that should honestly make you angry. Because once you see what's actually happening inside an atom, you'll realize that almost everything you think you understand about the physical world is built on a foundation of convenient lies. And the truth is so bizarre that your mind will literally resist accepting it. So let's tear down the comfortable fiction and rebuild it with what's actually there. And I'm telling you right now, you're going to hate parts of this, because what we're about to discuss doesn't just challenge your understanding, it challenges the very idea that understanding is even possible. Start with hydrogen. The absolute simplest atom in existence. One proton sitting in the center, one electron somewhere nearby. Elementary school material. Right? Your mental picture probably has that electron traveling in a neat circle around the proton like a tiny moon orbiting a tiny planet. So here's the first question that destroys everything. At this exact moment, where is that electron located? Your instinct says, well, it's currently on one side of the atom moving along its path, and in a fraction of a second it'll be on the other side. Seems reasonable. Seems logical. Completely wrong. The electron doesn't have a location. Not because we haven't measured it carefully enough. Not because our technology has limitations. Because location itself isn't a property the electron possesses until something forces it to have one. This isn't me being poetic or mysterious. This is what every single experiment ever conducted has confirmed. The electron exists in what physicists call superposition. It's simultaneously distributed across multiple positions at once. Not probably here or possibly there, actually genuinely in multiple places at the same time. There's a probability cloud surrounding the nucleus, and the electron is that entire cloud. Now you're probably thinking, okay, so it's like a fog. The electron is stretched out and thinly spread across a region of space like spray paint on a wall. Still wrong. The electron isn't smeared out. When we actually detect it, we always find a point, a single location, never something fuzzy or distributed. What's spread out isn't the electron itself, but the likelihood of finding it in various spots. There's this mathematical function, the wave function, that tells you the odds of detecting the electron at any given position. High values mean high probability. Low values mean low probability. 0 means impossible. You will never find it there, no matter how many times you look. But here's where your brain starts breaking. Before you measure, the electron isn't secretly hiding in one of those high probability zones. It's not like the electron is actually in a specific spot and you just don't know where. It genuinely has no definite position. The wave function doesn't describe where the electron is. The wave function is the electron. That's the entire story. Now let's address the elephant in the room. These supposed orbits. You've got this image of the electron racing around the nucleus in a circular track, looping endlessly like a car on a race course. Maybe fast, maybe slow, but definitely following a path. Here's why that picture self-destructs the moment you think about it seriously. Anything moving in a circle is constantly accelerating. Even if the speed stays the same, the direction keeps changing, and changing direction is acceleration. That's basic physics. Nothing controversial there. Now here's the problem. When charged particles accelerate, they emit electromagnetic irradiation. They throw off energy in the form of light. This isn't theoretical. We observe it constantly in particle accelerators and other systems. It's one of the most confirmed phenomena in all of physics. So if the electron were actually circling the nucleus, it would constantly be hemorrhaging energy, radiating it away as electromagnetic waves. And as it loses energy, The orbit would decay. The electron would spiral inward, moving faster and faster as it gets closer to the nucleus until finally it crashes into the proton. How long would this catastrophic collapse take? You can do the math yourself. The answer is roughly 1/10 of a trillionth of a second. If atoms actually worked the way your textbook picture suggests, every atom in the universe would have disintegrated before you finished reading this sentence. Obviously, that's not happening. Atoms are stable. They persist. So the electron cannot be orbiting. That explanation is dead on arrival. Fine, you say. Maybe the electron isn't moving. Maybe it's just stationary, held in place by electrical attraction. Also impossible. If the electron were sitting perfectly still, we would know its exact position. Right there in its exact momentum, 0, not moving. But quantum mechanics has this iron law called the Heisenberg uncertainty principle. You cannot simultaneously know both position and momentum with perfect precision. Not because our instruments are inadequate, because nature itself forbids it. The more precisely you pin down where something is, the less precisely you can know where it's going. The more precisely you know its motion, the less you can know about its location. You cannot have both. So the electron isn't orbiting and it isn't stationary. What is it doing? Nothing. It's not doing anything in the sense you mean. It exists as a wave function, a mathematical description of probabilities. And this wave function can only take certain specific shapes and energies. We call these allowed configurations orbitals, not orbits. Orbitals, and an orbital is not a trajectory or a path. The electron follows. It's a probability map showing where you might detect the electron if you perform a measurement. The ground state orbital of hydrogen is spherically symmetric. The probability peaks at the nucleus and gradually decreases as you move outward. There's no loop, no circuit, just a hazy cloud of might be found here. Higher energy orbitals get weirder. Some look like barbells. Some resemble inflated donuts. Some have complex lobes pointing in different directions. These aren't tangible structures you could touch. They're probability distributions, statistical maps of detection likelihood. And when an electron transitions from one orbital to another, it doesn't smoothly glide between them. It doesn't travel through the intervening space. It jumps instantaneously. One moment the wave function has the shape corresponding to orbital A. The next moment it has the shape corresponding to orbital B. No intermediate stages, no journey. It's called a quantum leap, and there's no mechanism, no explanation for how it happens. The mathematics describes it, experiments verify it, but there's no story you can tell about the electron taking a path from here to there, because it doesn't take a path, it just changes. Let's talk about what an electron actually is, because this is where things get properly disturbing. You think of it as a tiny sphere, incredibly small, but still a definite object with a shape and size, except experiments keep showing us that the electron also behaves like a wave. It interferes with itself, it diffracts around obstacles, it spreads out and recombines. All the characteristic behaviors of waves. So, which is it? A particle or a wave? The answer is neither, and that's not a cop-out. The electron is a quantum object. It's something that has no equivalent in the everyday world you experience. It exhibits particle-like properties in certain experimental setups and wave-like properties in others. But fundamentally, it's neither. It's its own category of thing. When you're not observing it, it's described by a wave function that evolves smoothly, interferes with itself, behaves like a wave in every mathematical sense. But the instant you measure it, the instant you actually detect its presence, you always get a localized result, a dot on a detector screen, a click in a sensor, never a spread-out wave. The measurement process collapses the wave function. The distributed probability cloud instantly becomes a single definite outcome. And nobody understands how this happens. Nobody knows what qualifies as a measurement. Nobody knows why observation changes the system. This is the measurement problem, and it's been haunting physics for almost 100 years. There are interpretations trying to explain it, many worlds, pilot wave theory, objective collapse models, but they're interpretations, not proven mechanisms. The equations work flawlessly. The predictions match reality to absurd precision. But we don't have a clear picture of what's actually occurring. Let's make this worse. Add more electrons to the picture. Helium has 2, carbon has 6, iron has 26. All these electrons exist simultaneously as wave functions in the atom. But here's the thing that breaks everything. Electrons are identical, not similar, not basically the same. Perfectly, absolutely, fundamentally identical. There is no property, no measurement, no possible experiment that could tell electron 1 from electron 2. They're not two different entities that happen to share characteristics. They're indistinguishable in a way that has profound consequences. If you swap 2 electrons in a system, the overall wave function changes sign. It picks up a negative factor. This isn't some minor detail. This is the Pauli exclusion principle, and it's the reason solid matter exists, the reason you don't phase through the floor, the reason atoms have structure and chemistry functions and complex molecules can form. No 2 electrons can occupy identical quantum states. If 1 electron is in a specific orbital with a specific spin direction, no other electron can be in that exact configuration. They stack up, filling different orbitals, creating the structure of the periodic table. Without this principle, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. No diversity, no complexity, no molecules. But why does swapping identical particles change the wave function sign? We don't know. It's just the rule we discovered through observation. The mathematics works. Reality agrees. But there's no deeper explanation available. Now the nucleus, you probably think that part is straightforward. Protons and neutrons clustered together like a bunch of marbles in a bag. Wrong again. Protons and neutrons aren't even fundamental particles. They're composite structures made of quarks. 3 quarks per proton, 3 per neutron, bound together by the strong nuclear force carried by particles called gluons. But the quarks aren't stationary inside the proton. They're quantum fields, fluctuating wildly, constantly interacting, perpetually exchanging gluons. The proton isn't a container holding 3 quarks like a box holds balls. The proton is a bound state of the quark field, a stable pattern of oscillation in a quantum field. And most of the proton's mass doesn't even come from the quarks themselves. Quarks have very little mass. Most of the mass comes from the energy of the quantum field binding them together. Mass equals energy, remember? So when you ask what's inside a proton, the honest answer is energy, field energy in a stable configuration, not stuff. Not particles, energy arranged in a pattern. Step back and ask the fundamental question again. What's really inside an atom? Not particles, not little spheres, not orbits, not objects. What's inside is fields, quantum fields permeating all of space. The electron field, the quark field, the gluon field, the electromagnetic field. These fields are everywhere, always, filling every point in space. When we say there's an electron in an atom, we mean the electron field has a localized excitation near the nucleus. The atom isn't a thing. It's a pattern. A stable arrangement of field excitations held together by forces that are themselves carried by other field excitations. There are no solid objects at the fundamental level, no stuff, only fields. And these fields are mathematical constructs. They assign numbers to every point in space-time. Numbers that evolve according to differential equations, numbers that occasionally produce localized disturbances we call particles. You hate this? I can feel your resistance from here. You want there to be something tangible at the bottom of reality, something solid you can point to and say that's what it's actually made of. But there isn't. There's mathematics, equations, symmetries, conservation laws, and miraculously, incomprehensibly, that mathematics generates the appearance of solid objects, tables, chairs, your body. All of it is patterns in quantum fields, held together by forces, stabilized by exclusion principles, flickering through configuration trillions of times every second. You've heard that atoms are mostly empty space. That's wrong too, because empty space implies nothing is there, but the quantum fields remain. Virtual particles constantly pop in and out of existence. The vacuum seethes with activity, and the electron's wave function fills the entire atomic volume. The electron is there in the sense that its probability amplitude is non-zero throughout the atom. When you push against a table, you're not feeling particles colliding. You're feeling electromagnetic repulsion between electron clouds. Field configurations resisting overlap, the Pauli exclusion principle preventing electrons from sharing quantum states. It feels solid because the forces are enormous, but there's no actual contact, no touching, just fields pushing against fields. Consider the scale. The nucleus is 100,000 times smaller than the atom. If you expanded the nucleus to marble size, the atom would span a football stadium, but the electron itself, as far as every experiment can determine, has zero size. It's a mathematical point. So you have a point particle with no dimensions, somehow occupying a volume 10 billion times larger than the nucleus. Does that make sense? Absolutely not. But that's what reality insists on being. Electrons have spin. It acts like angular momentum, like the electron is rotating. But the electron cannot be spinning because it's a point. Points have no extent, nothing to rotate, yet the electron possesses angular momentum, intrinsic angular momentum that doesn't arise from motion. It's just a property it has, like charge or mass. We call it spin because mathematically it behaves like angular momentum, but it's not actual rotation. This spin is quantized. Always one of two values, up or down along any axis you measure. Never intermediate values. And before measurement, the spin doesn't have a definite direction. It exists in superposition. The moment you measure it along one axis, it becomes uncertain along perpendicular axes. Nothing in your daily experience behaves this way. Energy levels in atoms are quantized. The electron can only possess specific discrete energies, not any arbitrary value. Why? Because the wave function must fit properly around the nucleus, like a vibrating string that can only resonate at certain frequencies. The electron's wave function can only accommodate certain wavelengths. Since energy relates to wavelengths, only certain energies are permitted. When electrons jump between energy levels, they emit or absorb photons carrying exactly the energy difference. This is why atoms emit light at characteristic wavelengths, why hydrogen produces its distinctive spectral lines. Each line corresponds to a specific transition. We can measure these wavelengths to extraordinary precision. We can predict them using quantum mechanics to extraordinary precision. They agree to 12, 14 decimal places. The theory works perfectly. But why is energy quantized? The mathematics tells us, the experiments confirm it. There's no deeper reason accessible to us. When you try to observe what's happening inside an atom, you face an insurmountable barrier. You can't use visible light because its wavelength exceeds the atom size. You need shorter wavelengths, higher energies. But high-energy probes disturb what you're trying to observe. They knock the electron out of its state. They change the very thing you're measuring. This isn't a technical limitation we might overcome with better instruments. It's fundamental. To see small things, you need short wavelength. Light, short wavelengths mean high energy. High energy means large disturbance. You cannot avoid it. There is no such thing as passive observation at quantum scales. This is why we can't say where the electron is before measurement. Not because it's hiding somewhere we can't see, because the property of having a definite location doesn't exist until a measurement forces it into existence before measurement. Wave function, superposition, probability after measurement, definite state, one possibility actualized. The measurement doesn't uncover pre-existing reality. It creates definite reality from probabilistic potential. So what's actually inside an atom? Not miniature solar systems, not particles in the intuitive sense, not objects, What's inside is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes, telling you what you'll find if you look, but describing nothing definite when you're not looking. The atom is a quantum system. Quantum systems don't behave like anything in your everyday world. They exist in superposition. They have fundamentally uncertain properties. They resist visualization. You cannot picture what's inside an atom because there's nothing to picture. The wave function isn't a physical wave moving through space. It's a function in an abstract mathematical space called Hilbert space, a list of complex numbers, encoding probabilities, information, not substance. And yet from this abstract mathematical structure, the entire physical world emerges. Chemistry, biology, consciousness, all of it constructed from patterns in quantum fields, governed by equations, following rules that defy intuition but work with staggering precision. This is what's really inside an atom, not particles, not stuff, mathematics, pure abstract, beautiful, utterly alien mathematics. And if that leaves you unsatisfied, if you still demand something more tangible and real at the foundation of existence, well, the universe has no obligation to meet your expectations. It is what it is. And what it is exceeds anything your ancestors could have imagined in their wildest fever dreams.